About the author. Stephen Hawking, the most famous and active physicist of our time, was the Lucasian Professor of Mathematics at the University of Cambridge. About this book. A Brief History of Time is Hawking's masterpiece and the most famous popular science classic in the world. It has sold more than 10 million copies and been translated into more than 40 languages. One of Hawking's postdoctoral students half-jokingly commented that Hawking's books sell better than Madonna's books about sex. Core content. In A Brief History of Time, Hawking introduced the basic knowledge of 20th century physics, covering a wide range of topics, from relativity to quantum mechanics, from cosmic expansion to elementary particles, and from black holes to wormholes. More importantly, Hawking also introduced his two most important academic contributions, the singularity theorem and Hawking radiation, as well as the boundless universe model, which attempts to solve the problem of the origin of the universe. Preface. Hello and welcome to listening to this book every day. This audio issue interprets for you a milestone in global scientific writing, Stephen Hawking's A Brief History of Time. The English version of this book has about 256 pages. I will spend time telling you the essence of the book. What contributions did Hawking make to the study of the universe? The book, A Brief History of Time, should be the most famous and best-selling popular science book in the world. After its publication in 1988, it appeared on the bestseller list for 237 consecutive weeks, which was 4.5 years, setting an unprecedented best-selling record. This book has been translated into more than 40 languages. It is said that on average, every 750 people around the world own a copy of A Brief History of Time. So, one of Hawking's postdoctoral students half-jokingly commented that Hawking's science popularization was more popular than Madonna's book on sex. When it comes to what a certain book is called, you must have heard it a lot, such as A Brief History of All Things, A Brief History of Humanity, A Brief History of the Future, etc. There is also a book called The World is Flat, which the subtitle of A Brief History of Time is A Brief History of the 21st Century. It can be said that A Brief History of Time pioneered this naming method. Stephen Hawking, the author of A Brief History of Time, is also the most famous and legendary scientist in the world today. This is because although Hawking suffered from amyotrophic lateral sclerosis, the ALS that came into everyone's attention because of the ice bucket challenge, and he was confined to a wheelchair, he still relied on his outstanding mind to make a huge contribution to contemporary physics, especially the study of the Big Bang and black holes. Hawking was the Lucasian Professor of Mathematics at the University of Cambridge during his lifetime, and the position of Lucas Professor of Mathematics was once held by top scientific giants such as Newton and Paul Dirac. Therefore, Hawking's academic achievements are indeed amazing. A Brief History of Time is not a thick book, with only more than 200 pages in the English version, but the book covers a wide range of content, from relativity to quantum mechanics, from cosmic expansion to elementary particles, from black holes to wormholes. So after reading this book, you may have a better understanding of science fiction movies like Interstellar, that involve many physical concepts. But to be honest, A Brief History of Time is not friendly to ordinary readers because Hawking only gave a brief introduction to many physics concepts, and some even touched upon it briefly. Readers without a certain knowledge base may not understand it at all. Some people even conducted a survey and found that after watching A Brief History of Time, the vast majority of people had forgotten all the content except the joke at the beginning. It is almost as if they have not watched it. So Hawking had to publish a book, A Brief History of Time, popular edition, in the hope that more people could understand his theory. Later, thanks to the 3-dimensional and 4-dimensional imaging technology of the Hubble telescope and computers, A Brief History of Time was released in an illustrated version, adding more than 200 color illustrations to the book, allowing readers to better appreciate the wonders of cosmology. As a classic popular science book, what is truly special about A Brief History of Time is that it introduces several of Hawking's own major theoretical contributions. First, Hawking and the British mathematician Penrose proved the famous singularity theorem, which is related to the general theory of relativity and the expansion of the universe. Second, Hawking proved that black holes can also emit radiation. This radiation is called Hawking radiation. Third, Hawking proposed a boundaryless universe model, believing that the universe has no boundaries, no beginning, and no end. This is a challenge to God. Hawking introduced these theories in A Brief History of Time, so next we will start with these theories to help you understand the essence of A Brief History of Time. The first question we need to talk about is, what is the singularity theorem proposed by Hawking and Penrose? The second question is, what is special about the boundaryless universe model proposed by Hawking? Let's look at the third question again. Why did Hawking say that black holes are not completely black? Part 1. Let's first look at the first question. What is the singularity theorem proposed by Hawking and the British mathematician Penrose? Before the 20th century, people believed that the universe was static, even though Newton's law of universal gravitation already stated that different objects attract each other. People still invented various explanations to maintain the assumption that the universe is static. Even Einstein stumbled on this issue. Einstein published the general theory of relativity in 1915, proposing that space and time can be curved. According to his equations, the universe is not static, but Einstein believed that there must be something wrong with this, so he forcibly added a cosmological constant to his equation, so that, according to the equation, the universe was stationary. But in the 1920s, when scientists were observing other stars, they discovered that many stars had experienced a phenomenon called red shift, which means that these stars were moving away from the Earth. Originally, people thought that the movement of these stars was just random. Some stars might be getting farther and farther away from us, while others are getting closer and closer to us. But in 1929, American astronomer Edwin Hubble, the astronomer who named the Hubble telescope after him, discovered that most stars were moving away from the Earth. The further away the Earth is, the faster they are leaving. What does this mean? Just imagine that if you take a balloon and draw a few dots at different locations on the surface of the balloon and then inflate the balloon, as the balloon gets bigger and bigger, the dots you draw will also become closer. Further and further, the further apart 2 points are, the faster they are moving away from each other. This balloon is actually equivalent to our universe. The points on the balloon are equivalent to the Earth and other stars. Most stars are getting farther and farther away from the Earth, which means that our universe is constantly expanding. After Einstein learned about this observational result, he discovered that the cosmological constant added to his equation was completely redundant. The universe was not static, but was indeed expanding. So Einstein later said that the cosmological constant was the biggest mistake he made in his life. After discovering the expansion of the universe, scientists found a new model based on Einstein's general theory of relativity to describe the expanding universe. This is the Friedmann model, because it was first proposed by a man named Alexander. Scientists have discovered through calculations that in the Friedmann model, if we push forward in time, the universe will shrink. If we push back to 15 billion years ago, then the distance between all galaxies will become zero, as if the entire universe was squeezed tightly into a point. This point is called a singularity, and it is the beginning of space and time in the universe. The nature of a singularity is very special, and we cannot intuitively imagine what it is. However, through mathematical calculations, it can be found that the volume of the singular point is infinitely small, the degree of curvature is infinite, the density is infinite, and the gravity is infinite. There are many infinities mentioned here, but mathematics cannot actually handle infinite calculations. This also means that although the Friedmann model is proposed based on the general theory of relativity, theories including general relativity have all failed at the singularity. So, Hawking said that the emergence of singularities proves that general relativity is only an incomplete theory because it failed at the very beginning of the universe, and general relativity predicted its own collapse. Now that we understand what the singularity is, let's take a look at what contribution Hawking made in this research process and how he views the singularity. When the theory of singularity was first proposed, not all scientists agreed with it. According to Hawking, Einstein himself didn't believe this statement. He believed that if we pushed the time forward, different galaxies would not collide with each other, but would be exactly staggered. Two other Soviet scientists also tried to prove that the singularity may be just a special case with a small probability in the Friedmann model and does not exist in the actual universe. A long time ago, between different galaxies, although they were indeed very close together, they were not exactly in the same place, so there was nothing strange about them. But after reading some research by mathematician Roger Penrose, Hawking believed that the singularity theory should be established. After several years of research, he and Roger Penrose used rigorous mathematical methods to prove that if the general theory of relativity is correct, and there are indeed as many stars, galaxies, and other matter in the universe as we have observed, then the universe is, a long time ago, it must have been born in a singularity. This was the beginning of the universe. This theory is called the Penrose-Hawking singularity theorem. Some people were initially reluctant to accept Hawking's research conclusion because they did not like the idea that the universe had a beginning. Others felt that this conclusion violated scientific determinism and ruined the perfect general theory of relativity. But there is no way, because Hawking and Penrose are not talking nonsense. They used mathematical calculations to prove this result down to earth. Mathematics cannot lie to people, and people cannot argue with mathematical laws. So since then, whether they like it or not, almost all scientists have admitted that the universe was indeed born in a singularity. What I just talked about is the first question. What is the singularity theorem proposed by Hawking and Penrose? Before the 20th century, people thought that the universe was static. It was not until scientists discovered that most stars are moving away from the Earth that people discovered that the universe is continuing to expand. When scientists studied the expanding universe model, they found that 15 billion years ago, the distance between all galaxies was 0. At that time, the universe was a singularity with infinitely small volume, infinite density, curvature, and gravity. The contribution of Hawking and Penrose is that they used rigorous mathematical methods to prove that if the general theory of relativity is correct, then the universe must have been born at such a singularity, which is the beginning of the universe. Part 2. The singularity theorem just mentioned is one of Hawking's greatest academic contributions. But later, Hawking changed his mind and proposed the unbounded universe model, believing that the universe does not need to be born in a singularity. So, let's take a look at the second question. What's so special about the boundless universe model proposed by Hawking? As mentioned in the first question, Hawking and Penrose proved the singularity theorem together. After that, almost all scientists admitted that the universe was born in a singularity. The moment when the universe was born is called the Big Bang, and this singularity is called the Big Bang singularity. The Big Bang theory is currently the most mainstream model describing the origin of the universe. Let's first take a look at what the Big Bang model of the universe is. In the Big Bang model, at the moment of the Big Bang, the volume of the universe was considered to be 0 and the temperature was infinitely high. After that, the universe began to expand rapidly and the temperature began to decrease. 1 second after the Big Bang, the temperature of the universe dropped to 10 billion degrees, which is probably the temperature that a hydrogen bomb can reach when it explodes. 100 seconds later, the temperature continues to drop to 1 billion degrees, and protons and neutrons begin to combine together to form atomic nuclei. After that, the temperature of the universe continues to drop and continues to expand in 1 million years. After that, the temperature of the universe dropped to several thousand degrees and atoms began to form. As the temperature of the universe continued to decrease, materials such as galaxies and stars began to form. Now, 15 billion years later, the universe has expanded many, many times, and the temperature has become very low. Is only a little higher than absolute zero, but the energy of the original Big Bang still remains in various places in the universe, and we can still observe it. Scientists call it microwave background radiation, which is like the background that fills the universe noise. Although the theory of the Big Bang sounds incredible, it is indeed consistent with our observational evidence today, so it has been widely accepted by scientists. But this theory still makes many scientists feel a little embarrassed. You see, you can feel from the description just now that the Big Bang is the starting point of the universe. All matter, even space and time, only appeared after the Big Bang. Any events before the Big Bang have no meaning to us or do not exist at all. In other words, the space and time of the universe are not infinite but have a very special boundary and beginning. This beginning is the Big Bang singularity. But the problem is, as we talked about in the first question, the Big Bang singularity is a very special existence. Here, all the laws of physics are invalid. People have no idea what will happen with this singularity. Something pops up, so how did the laws that the universe follows now come into being? Who sets these laws? Is it really God? Scientists currently do not have a good explanation for this problem, which also leaves a glimmer of hope for the religious community. Hawking said that in 1981, the Catholic Church in the Vatican invited many scientists to hold a cosmology conference. After the scientists finished their speeches, the Pope said that you can study the various historical laws after the Big Bang. But you scientists should not study the moment of the Big Bang, because that was the moment when all things were born. That is God's business, and you should not interfere with it. Hawking also delivered a speech at this conference. The theme of his speech was the borderless universe model. After hearing what the Pope said, he muttered in his heart, saying that it seemed that the Pope did not understand what I said. Because the boundaryless universe model he proposed means that the universe has no beginning and no moment of birth. There is no place for God. Why did Hawking say this? Let's take a look at what's going on with the boundaryless universe model he proposed. When we mentioned the singularity theorem and the Big Bang model before, we always had a premise. That is, if the general theory of relativity is correct, but this premise may not be tenable. This does not mean that general relativity is wrong, but that it is an incomplete theory and is not combined with quantum mechanics. In the 20th century, the two most important discoveries in physics were also the two core basic theories of physics today. One is the theory of relativity, and the other is quantum mechanics. Generally speaking, the theory of relativity governs macroscopic fields, such as the motion of galaxies, etc., which fall under the theory of relativity. Quantum mechanics governs the microscopic realm, such as particle motion problems, which fall under the management of quantum mechanics. When studying general issues, these two sets of theories are incompatible with each other, but Hawking believes that when studying the Big Bang singularity, it is necessary to combine relativity and quantum mechanics. Hawking believes that the singularity theorem has actually proven that general relativity can no longer describe the universe well under extreme circumstances, such as the Big Bang singularity. At this time, quantum effects must be taken into account. On the basis of general relativity, there are only two possibilities for the universe. Either it exists for an infinite time, or it has a beginning like a Big Bang singularity. But if quantum mechanics is introduced, a new possibility will appear. A finite and unbounded universe. Finite and unbounded means that the universe and space-time are finite, but have no boundaries. What does that mean? Hawking made an analogy using the Earth. Our Earth is a finite planet, and we know its diameter and size. However, the Earth has no boundaries or beginnings. If you keep walking on the Earth, you will not be able to find a boundary or fall outside the Earth. The universe in Hawking's boundaryless universe model is a four-dimensional universe composed of space and time intertwined. In this universe, space-time is like the surface of the Earth, which is limited in scope, but does not form boundaries or singularities. Every point in space and time is just like a certain point on the Earth. There is nothing special. The laws of science are applicable at any point in space and time, and no collapse will occur. In the unbounded universe model, the universe does not have a special singularity, and there is no need for God to specify a special law. According to Hawking, this universe is completely self-sufficient and is not affected by any external things. There are no moments of creation or disappearance. It is existence itself. In this way, the universe does not need God to create it. It should be noted that Hawking himself also emphasized that the boundaryless universe model is still just an idea, which is equivalent to his own opinion. The current mainstream model of the universe is still the Big Bang model. Of course, the boundaryless universe model is not just a fantasy. It is an attempt to combine quantum mechanics and relativity, and it is also a scientific theory that can be tested. At this point, you already know what is special about Hawking's boundaryless universe model. In the mainstream Big Bang model of the universe had a beginning, and this beginning was the Big Bang singularity. But science doesn't have a good explanation for what happened at the moment of the Big Bang, and that leaves a place for God. In the boundaryless universe model, Hawking combined quantum mechanics and relativity and believed that our universe's space-time is limited in scope but has no boundaries. Therefore, there is no singularity or beginning, and there is no need for God to create it. Of course, the boundaryless universe model is not currently mainstream, but it is a scientific theory that can be tested. Part 3. The first two questions are related to the Big Bang and the singularity of the universe. In addition to this field, Hawking's other most important academic contribution is the study of black holes. So, for the third question, let's take a look at the contribution Hawking made to the study of black holes. Why did he say black holes are not that black? Let's first take a look at what a black hole is, starting with the principles of stars. We all know that there is a gravitational force between substances, and the greater the mass of the object, the greater the gravitational force it has. Stars like the Sun have very strong gravity. Affected by their own gravity, stars will have a tendency to collapse inward, that is, to collapse on themselves. So if that's the case, why is the Sun still so big after so many years? It didn't collapse due to gravity. This is because there is a supporting force inside the Sun that can balance gravity. The temperature inside the Sun is very high. The fierce collision between hydrogen atoms with atomic number 1 will combine to form helium atoms with atomic number 2. This process will release huge energy, which is equivalent to countless atoms inside the Sun. Hydrogen bombs continue to explode, which will provide a supporting repulsive force for the Sun. In this way, when the Sun's gravity and supporting force balance each other, the star can remain stable. So, the Sun has not collapsed yet. Then the question arises, the supporting force inside the star is supported by hydrogen and other nuclear fuels, but sooner or later, these fuels will burn out. Once burned out, the star will continue to collapse under the influence of gravity. What will happen at this time? There are several possibilities for the final destination of stars. If the star has a small mass, its gravity can balance with the repulsion of the internal particles, and it will eventually become a neutron star or a white dwarf. However, if the star has a huge mass, larger than 1.5 suns, then its internal repulsive force is not enough to offset its gravity. In this case, the star will continue to collapse and become a black hole with an extremely massive mass and an extremely small volume. Once we understand the formation principle of black holes, the properties of black holes will be easier to understand. The biggest characteristic of a black hole is that it has extremely strong gravity. Any matter, including light, can never escape the black hole as long as it enters a certain critical area. From the outside, if even light cannot escape, a black hole is, of course, completely black, which is why it gets its name. But the problem is that the property of black holes that attracts everything conflicts with the second law of thermodynamics. According to this law, black holes should also have a temperature. Objects with high temperatures will emit radiation and particles, and black holes should be no exception. But as I said just now, even light cannot escape the gravity of a black hole, so how is it possible that particles can escape from a black hole? Isn't this a contradiction? Scientists, including Hawking, are confused by this question. But using quantum theory, Hawking successfully answered this question. He found that black holes do emit particles, but these particles do not escape from the black hole but emerge from the empty space at the edge of the black hole. To understand Hawking's statement, the most critical point is to understand the uncertainty principle in quantum theory. According to this principle, when we measure the behavior of particles, gravitational fields, or electromagnetic fields, we will find that if we measure one physical quantity more accurately, the measurement of the other physical quantity will be less accurate. For example, the more accurately you measure the speed of a particle, the fuzzier your understanding of the particle's position becomes. It is impossible for humans to grasp the precise position and speed of the particle at the same time. According to the uncertainty principle, even an empty space that seems to contain nothing is actually undulating on a microscopic level. Think about it. If a space is completely empty, it means that the intensity of the gravitational field or electromagnetic field in it is zero, and the rate of change is also zero. These two physical quantities are determined at the same time. This obviously violates the uncertainty principle and is impossible. What is there in that empty space? It's very magical. In empty space, pairs of particles are actually produced all the time. In order to maintain energy conservation, some of these particles have positive energy and some have negative energy. When they collide together, they will be annihilated at the same time. At this point, we can take a look at what Hawking's explanation means. Hawking proposed that although the edge of a black hole appears to be void, it is actually constantly producing pairs of particles all the time. Particles with negative energy among them will be sucked into the black hole. But there are also some particles with positive energy that can luckily escape from the edge of the black hole and go to other places. If we stand outside a black hole and look at it, it seems like the black hole is constantly emitting particles outward. This is black hole radiation, also called Hawking radiation. It is precisely because of the existence of this radiation that Hawking said that black holes are not actually completely black. Hawking radiation is a very valuable theory in physics. Because the birth of a black hole is calculated using general relativity, the radiation of a black hole is related to quantum mechanics. In other words, Hawking radiation is an attempt to combine general relativity, quantum mechanics, and thermodynamics. Therefore, although Hawking radiation has not been observed yet, it still has a high theoretical value. At this point, you probably understand Hawking's contribution to the study of black holes. Hawking proposed that although the gravity of a black hole is so great that even light cannot escape, the black hole is not completely black. According to the uncertainty principle in quantum theory, pairs of particles will continue to be generated in the void at the edge of the black hole. Negative energy particles will be absorbed by the black hole, but some positive energy particles will escape from the edge of the black hole. To the outside world, it looks like a black hole has been emitting particles. This is black hole radiation, also called Hawking radiation. Summary. At this point, you will understand the essence of A Brief History of Time, that is, what contributions Hawking made to the study of the universe. Let me summarize it for you again. The first issue we talk about is the singularity theorem proposed by Hawking and Penrose. A singularity is a point with infinitely small volume and infinite density, curvature, and gravity. Hawking and Penrose used rigorous mathematical methods to prove that if the general theory of relativity is correct, and there is indeed as much matter in the universe as we observe, then the universe must have been born in a singularity. For the second question, we talked about the boundaryless universe model proposed by Hawking. In the current mainstream Big Bang model of the universe has a boundary and a starting point, which is the Big Bang singularity. But at the moment of the Big Bang, all scientific laws broke down, so scientists still can't figure out why the universe must be the way it is. Some people say that it was the moment when God created the world, so it cannot be explained by science. Different from the Big Bang model, Hawking introduced quantum mechanics into the boundless universe model, believing that the universe has no boundaries, so there is no singularity, no beginning, and no end. In this way, there is no need for God to create creation, the universe. In the third question, we talked about Hawking's research on black holes, which is Hawking radiation. Hawking proposed that black holes are not completely black, and they also emit radiation. According to the uncertainty principle, the void at the edge of a black hole is actually not completely empty, but will continuously generate pairs of particles. Some of the particles are absorbed by the black hole, but some escape from the edge of the black hole. This is equivalent to the black hole emitting particles outward. This phenomenon is called black hole radiation, also known as Hawking radiation.